Okay, Assalamualaikum and good morning. I hope you can see my screen. Okay, good. So I was trying to see what's going on. Okay. Right. Let's recall what we did. Uh, Let me just go to the point where we left. Okay. I think the last thing that we did was something about uh, RLC circuits. So one of the things that I sort of mumbled because I could not remember precisely is the idea of uh, what happens to the current uh, uh, when it passes through some uh, electrical circuit elements. And let me just give this particular web page. You can actually see, hopefully, can you see the web page now? Everyone? Yes or no? Are we still in class? Okay, sorry about that. It seems that the faculty's Wi-Fi is unstable, so I'm now on my broadband data. So, are you hearing me, guys? Can anyone answer me? Okay, great. So I'll restart. Okay, let me present back. Okay, can you see my screen now? Someone? Okay. So, okay, great. Thanks. Sorry about that. The starts having problems over here. So, okay, let me just remind you that we did this kind of application of complex numbers to the case of electrical circuits. I'm not sure whether I mentioned it. This is applicable for the case of alternating circuits where you have oscillatory electrical signals. So then you will be able to see uh, the, the complex nature of the current in some sense or the voltage signals. Okay, and I did mention about certain things happen when you pass it through say electrical circuits elements. For example, uh, in the case of a just a simple resistor, pure resistor, then you know from the case of again, just check what's happening. So in the case of resistor, so this will be now oscillatory. Okay. And we shall look at the case of how do you define oscillatory functions using complex functions after this. So, and then this is, yeah. Oh, okay. So what do I do here? Let me leave the meeting first and then I'll come back. Okay, and let's see what happens. Can you hear me now? Better? So is my voice clear?
Still breaking from time to time.
Okay, it's probably my data is no the broadband thing. Let me change the. I'm just afraid to use the. Oops. Am I still with you? Okay, great. So I'm back using my the faculty's Wi-Fi. Is it clear now?
Yes, better. Much better.
Okay, so probably it's just my data is not so good. Okay. Uh, where am I? Okay. Yes. Regarding the. Oops. I've not shared my screen. This is what happens, and sort of leave and present now. I'm sorry, the Wi-Fi seems to be a bit slow today. Can't seem to be able to present now. Again, lost connection. I'm not sure what to do now. Are you still with me? Am I still with you? Okay. I switched to a different Wi-Fi connection. Hope that will not cause any problem anymore. So let me share my entire screen. And probably I will just uh, not show my own self. So I'll stop my, so you probably get a better reception. So, okay, now can you see my notes? Okay, great. So, remember what happened was in the last lecture we had mentioned about usage of complex numbers to electrical circuits, and this is only applying to the case of the alternating current, because then you would have, for example, your voltage to be oscillatory, and this can be represented by some complex oscillatory function. So then you'll see in the case of this V equals IR, here your R over here is going to be constant, okay, and hence your oscillatory signal from the voltage will be in sync with your oscillatory signal of your electrical current. Okay? So in that case, there's no lagging or there's no leading of signal. But once you introduce things like capacitors and inductors, then you see, for example, the reactance involve this kind of formulas. And let me go to the web page because I normally forget this. I never memorize these facts. For example, in the case of are you seeing the web page? Okay, great. So here is an example. So you can look up this allaboutcircuits.com. So you can see, for example, here is a pure inductive circuit. Let me just scroll this up. So you have a pure inductor circuit. Then what happens is you have an voltage here passing through the inductor, but then when you try to measure the current is actually lagging. Okay, so what happens in terms of the signal? Oops, sorry. What happens in terms of the signal? Here is your voltage, but then you don't have your current following that, but it sort of lags behind. It follows the same signal, but it lags behind. Okay, so that is what I mean by lagging, and the other one would be leading. This is the case of your capacitor. Okay, so this would be your voltage, and that is charging the capacitor. So you seem to see this signal, the current signals doing like this, and this is it's saying that the current is leading the voltage because it seems to have this pattern before that pattern. So you can look it up in, I think, in your first year notes or something. Okay, probably in a different course. Okay, let me go back to my notes. So now we would like to go to something different today. Is to look at powers of complex numbers, and then you can, from powers you can also talk about roots, which is just the inverse of powers in some sense, the inverse map of power. Okay, let's recall the case of your sine and cosine function, for example. Your sine and cosine function, you have seen before this in terms of the power series that your sine function are just the odd powers of the odd powers of your variable, and then your cosine function are just the even function of your even powers of your variables. Okay, but the other important thing is the alternating sign. You have a minus, you have a plus, you have minus, and then here you have minus, plus, minus, and so on. So you have alternating sign, and you have the sort of even degrees or odd degrees. So how can you get this? Well, okay, I'm showing you a slightly different function now. If I were to expand your exponential with I theta, what's going to happen is, okay, remember the exponential function is just e to the x equals to sum x to the n over n factorial. Okay, but now if I include I over here, then you will have I to the n. Okay, so in other words, what happens when you have that, your i's will start to flip signs. Your I will start to flip signs, and then you get your plus, minus, minus, plus, and then when you collect the even powers over here, and then you take the imaginary part, and then the odd powers over here. Okay, so in other words, you're collecting the real components together and then the imaginary components together, and what you get is precisely the power series expansion of your cosine over here. That's for the real part, and then for the imaginary part you have your what you call the sine power series. Okay, so in other words, one could now write this famous formula called Euler's formula, which is saying that, okay, your exponential I theta is equals to cos theta plus I sine theta. Okay, so this will be a useful tool when you do some kind of calculations with complex numbers. Okay, So what happens over here, you can almost see that, okay, this is going to be important when you have polar form. Okay, so remember we had mentioned before, let me just write down over here, when you use the Cartesian form, where you have the what you call real part plus imaginary part. Okay, so real plus imaginary thing. Okay, so this is what we call the Cartesian form. This is going to be this form will be friendly to addition. Okay, so meaning if you add two complex numbers, then you have the real components added together separately with the, okay, so you find that your Cartesian is much better to handle addition. But when you do the case of the polar form, the addition is, well, I mean, it's going to be a bit involved compared to the Cartesian case, but the polar form will allow multiplication to be done in a much simpler manner. Okay? We will see that this is why when it comes to doing powers, for example, what are powers? Powers are just simply multiplying the same number several times, and then you find that it's much better to do this in a polar form. Okay? So this is what we're going to do. Okay? So we're going to use the polar form over here, okay, to do multiplication. For example, over here, then you can see that suppose I have r equals to 1, then you see the so-called arguments over here will just simply add up. Okay. And when you do division, then this thing will be subtract. Okay. So when you multiply two numbers together, two complex numbers together, then the absolute value, this will be the absolute value, okay, this one, so the absolute value will just multiply each other, and then your exponent will also multiply, but then the effect is just like an addition of the phase. This is sometimes called the phase. Okay, so same thing when you do division. Division is just an inverse operation of your multiplication. So what you do in this particular case, the absolute part sort of gets divided, okay, and then the phase will just get subtracted. So you can see the simplification with respect to multiplication and division when you do polar form. In particular, you probably have seen this theorem before. It's called the Marvelous Theorem, where what you do is to make this connection of what you call powers of let me just, okay, sometimes, okay, let me just go back a little bit. Sometimes this is the short form, what you call, shorthand notation for this is sometimes called Cs, which is just cos plus I sine thing. So this is Cs theta. So what happens over here, you have Cs theta to the n, okay, and you can see that this is immediately related to cos n theta plus I sine theta. You will not see this directly from here, but you can see it directly from here, okay, because it's exponential. I theta is Cs, okay, and then you take the power of n, then simply when you take the power, you just multiply exponential I theta n times, that simply just add the I theta n times. Okay, so you get exponential I n theta. So now what happens over here, you get this possibility of doing this formulas for, say, double angle formula. You remember, what is it? Cos 2 theta, for example, is what? Cos squared theta minus sine squared theta. Okay. And then sine 2 theta will be what? 2 sine theta cos theta. Now, how do you get this? Well, you can simply use this the Marvelous Theorem. So you do a square of this, and then you find that when you do the square of this, you get cos squared, and then your I squared becomes negative, and then you get minus sine squared, and that gives the real part, and the imaginary part will give you that. Okay, so you can now start to think of, okay, I'm not just limited to double angle formula. You can do any multiple angle formula, and it's quite easy to do. Of course, to get the real part and the imaginary part, so that you get the formula for that, you still have to do the expansion. But the expansion, you can actually do it if you want to do it. For example, let me go to Wolfram Alpha. Again, no, these are just tools that can help you do things. Okay, so let's suppose I want to do this. Okay, let's do a simple one first. Are you seeing this? Great. Okay, of course this is simple enough. It's not calculating. Okay. So of course you know how to expand a quadratic expression over here. Okay, what we're interested here is just that. But suppose I have something much more complicated. For example, let's take 100. Now you don't want to do this by hand, but you are now able to use this tool to actually get all the expansion. So you don't need to, you have now tools that actually help you do things. Okay, right. Okay, so of course here we are assuming that your n over here is an integer. Okay, that's another thing, but you can actually generalize this. Okay, but the one thing that we want to do for this particular section is to do the inverse operation of the power, which is the nth root. So when you take the nth root, it's again the same thing. No, you just take the powers of your absolute value, in this case, okay, your r, when you write in terms of polar form. So you get r to the power 1 over n, and then you have exponential I theta to the power 1 over n. But then your exponential I theta power 1 over n is just like the one before. It becomes simplified like that. Then this will be just exponential I theta divided by n rather than multiplied by n. Okay, so again you have this simple formula that you can actually use to evaluate what I call nth root of a complex number. So let's look at some example. I think everyone knows how to do this. One of the standard examples that you must know almost immediately, without thinking too much, is when you have cases like what happens to certain angles. Okay, in this case over here, okay, this is not pi over phi is not something that you always do, but what happens when you do power to, say, power 25, then pi over phi in terms of exponential over here will be multiplied by 25, and then you get exponential I phi pi. Now, I want you to memorize in some sense or make it automatic. Whenever you find these values, certain integer times pi, taken the exponential I complex of that, you always know what's the value. Okay, so in other words, over here, since this is actually odd, I know that it's going to be -1. But you can do all this kind of intermediary steps, which is not really necessary. What I'm saying is you should now, no, if you can't do it, if you can't memorize it, then you do the intermediate steps. But if you can memorize it, much better. But you always have to check, okay? Even though you memorize, sometimes you memorize the wrong, you understand the wrong thing. So that's one thing that you have to be careful about. Okay, I think that should be much more, okay, this is much more interesting. So now let's suppose I've been given this question of find the cube root of 8. Okay, so you probably know that, okay, I know that that's just 2, because 2 cubed equals to 8. So I take the cube root of 2 will be a cube root, sorry, the cube root of 8, sorry, the cube root of 8 is 2. But this is just thinking of doing the nth root, okay, in this case cube roots, with respect to real numbers. Okay, but if you think the real numbers, remember that real numbers are essentially a subset of your complex number. So if I really think of your 8 over here as belonging, say, to C, then I would have different values besides 2. If I think of 8 belongs to R, then 2 is only the value. Okay, so how can you actually get the other values? Well, one needs to write this in terms of this. So, okay, 8 equals to 2 cubed, right? But then you remember that I can always add, multiply by a 1. This is just equals to 1. Okay, exponential I to n pi, even integers times pi, okay, that is always equals to 1. So it doesn't do anything, but it does add this phase. So when you write that in that manner, so you take 2 cubed exponential I to n pi to the power of 1 over 3, okay, of course you get your 2 back, okay, over here, but then you also have this, okay, and exponential I to n pi over 3, you can have different values depending on what n is. So normally we start with 0, for example. Okay, I have 0, then this will be just 1. But if I put n equals to 1, or plus minus 1 if you want to, if I put n equals to 1, then I have 2 pi over 3. Let's recall where that is. This is 0, this is pi over 2. Where's 2 pi over 3? What's 2 pi over 3? Can somebody give in that's in radian in degrees? That would be 360 degrees divided by 3. That would be 120. So it will be somewhere here. This is what? 2 pi over 3. Okay, so that, okay, now I found a different root which is different from 2, right? So that is one of it, but we also have another one because I can go further. N equals to 2, then I will get, for n equals to 2, I will get 4 pi over 3. Okay. I think 4 pi over 3 will be somewhere, it will be 2 pi, pi over here. So this will be 4 pi over 3. It's pi plus 1, pi plus pi over 3. Okay, so this is 4 pi over 3. Okay. Now, what about other values? Well, if I go to the other values, let's say 3, n equals to 3, then I get what? Exponential I 3 times 3 pi over 3. Is that right? Sorry, what am I doing? N equals to 3, that means EI 2 times 3, okay, times pi. But that is simply equals to exponential even numbers times pi is just simply equals to 1. And then the next one will be EI 2 4 pi, which is 8 pi. So I can write this as, sorry, divide by 3. Okay, I forgotten. Oh, why am I doing this? Divide by 3. I'm trying to explain. I 8 pi over 3. So 8 pi over 3, I can get that from what? That will be 6 pi, EI 6 pi, pi over 3, sorry, that's 2 pi, okay, EI 2 pi times, so that gives you 6 pi over 3, and then this will be 2 pi over 3. Okay, and you get back to this condition. And then you go further for n, this is n equals to 4, and you go for n equals to 5, you get that. Okay, but please check this so that you can see, okay, it's going to be just repeating all over again. So all you need is just, okay, I can only need to consider the case of when n is less than or equals to 3. Okay, so in this case, then I will have that, okay, to be my roots. So this is, after this is just repeating itself. Okay, so this will be the numbers. And if I want to convert to the Cartesian form, what is 2 pi over 3 is cos 120 degrees is what? Anyone? It will be 2 times a half plus I root 3 over 2. Okay, so you, no, those kind of things I need you to do automatically because you know you have done this before many times. And if you plot this on the complex plane, and it looks like this. Okay, so you have the real part over here, and if you look at the the real root, so this is the real root, but the complex root occurs in over here, and it seems to be like another one which is related to the top one by reflection. Okay, and this is just saying that, okay, what I'm going to get is the following. I get 2 times half plus root 3 over 2, and the bottom one is half minus I root 3 over 2. So you can see that these two roots are actually related by conjugation. And the other observation that you need to see is when you do cube root, the number here is actually 3, okay, 1 over 3, z to the power 1 over 3, and you are expected to see three different solutions according to this number. So if I do higher order roots, then it will always correspond, let's say n root, then I will expect to have n different solutions, n different roots, okay? And if n is even, then the roots will come in pairs. If n is odd, okay, because when n is odd, there will be at least one real root, okay, like the case of this cube root just now. So you have cube is actually n is odd over here, then you have one real root and then one single complex pair, okay. The complex roots always comes in pairs. Okay, and then the other thing, probably a geometrical thing, you can see that when you do the cube root thing, here you can see your angles are divided equally into 3 parts. Okay. 2 pi over 3, 2 pi over 3, 2 pi over 3. Okay, so you can see, okay, the distribution here is on a circle. Okay, this is on a circle of radius 2, which is the absolute value, your r equals to 2. Okay, and then the points will be distributed equally, so equidistant apart on the circle. Okay, so it's quite a nice geometric behavior. Okay, so this is what I mentioned just now. When you take the n root, we always get n different roots, with the complex roots being in pairs. Let's do a slightly more complicated one, where your z here, the number that you want to take the roots are essentially complex numbers. Okay, so here is given by minus 8i. So what you need to do is to find in this case it's a 6th root. Okay, so I would now need to convert this into your polar form. This is now in Cartesian form, so there's no real part, there's only imaginary part here. So I convert this into a polar form. So you have to remember now, okay, your exponential I 2 pi is 1. So if I take exponential I pi, it's going to be what? It's be cos pi plus I sine pi. So I sine pi is 0, cos pi is what? Anyone? Nobody? You should memorize this, please. Cos pi is minus 1. Okay, and then exponential I pi over 2, that should be I, and then you have another one, exponential I 3 pi over 2, that should be minus I. So these are the 4 special polar forms that you need to remember. Now what I need over here is minus I, so I should be getting this. So what do? I put 8 times exponential 3i pi over 2, and then of course I can add 2n pi, because exponential 2n pi, okay, is like exponential I 2 pi over here. Okay, so it gives you 1. So I can always add that. So once you do that, then when you take your n, you take your 6th root, then you will get different values for this. Okay, so you do this for yourself just to convince it. You enumerate your different n, then you get all these 6 different roots. Okay, and this is, you can see that this again, it lies in the circle of radius 2. Okay, is it radius 2? Radius square root 2, sorry. Yeah, 6 root. Sorry, get confused a little bit. A circle radius square root 2, and then you have the points, so you can plot one by one of the roots where they are. Okay, and they are equidistant apart on the circle. And you can try to find out what's the angle of this, what's the angle of that, what's the angle of that, and they are all the same. Okay. But the main thing here, no, I mean, this you need to work out a little bit, but the point is you always have the 6 roots. Okay, so this one will come in pairs, this will come in pairs. So which is the pair in this case? So I need to reflect that. I need to reflect that. Hang on, getting confused here. 1 plus I. So I will need a 1 minus I. Oh, no. Sorry, I'm getting confused. Again, you probably have to see it differently. So here, yeah, sorry, I got confused. This is, okay, I've left this for so long. Okay, there are 6 different roots. This is 1 root, 2 root, 3 roots, and then the other 3 is coming from the minus. So that is minus 1 minus I. Okay, so that would be the one which is the conjugate of 1 plus I. Okay, sorry about that, the confusion there. Right, I think that's enough for the complex root. How much time do we have? We have about 10 more minutes left. So let me just begin the next lecture so that we'll start off somewhere. Hello? Again, okay. Dah lama ke? Okay, let me just check. Oh, this has been, where did I stop? Can you hear me? Anyone? Am I back in the room?
Doctor, I think you are still lagging.
Okay, yeah, but I don't know what else I can do. This is on faculty Wi-Fi. If I use my data, then it will be my voice breaks up. So I'm not sure what to do now. Okay, let me just go back to the notes and see where precisely they are stopped or get disconnected. Hello. Maybe I should shut off my video. Yeah.
Scroll lagi sekali, lecture notes tadi tu.
Okay. I've done this, right?
Sebenarnya baru sampai muka surat 12 ni saja. Lepas muka surat 12 tu dia macam tiba-tiba disconnect.
Okay, okay. So this one I've completed, right? Okay, so let me just go to this one. So this one will be a slightly more complicated case. So it's good that you miss out all my mistakes just now. Okay, so we are looking at the case of taking the sixth root. Can you hear me now? Hello? Okay, because I can't see you guys. Okay, the sixth root, but now you take your z to be a bit more complicated than the one before, which is written down as a pure imaginary number. Okay, so in this particular case, it's not as obvious as before, where you take the cube root of 2, you know, a cube root of 8, you know, it's going to be 2 is one of them. But here you don't. Okay, you don't really have that. So what do you do in this particular case? You need to convert this. This is still in Cartesian form. Okay, so you need to convert this in a polar form so that you can do the in this case the sixth root. Okay, and the thing that you need, the thing that you need to do is always memorize this. Okay, because this will help you how to convert a Cartesian form to this polar form easily. So here you can see that, okay, if I just think in terms of what is the complex number here, is minus I. So, and then your 8 will be the absolute value, okay? So minus I is coming from exponential I 3 pi over 2. So I can plug that thing. So the z is going to be 8 times exponential I 3 pi over 2. But then remember, we can always add 1 or always add, sorry, multiply 1. And multiply by 1 anything which is even integer over here is always 1. So I can always do that. Okay? So then here you can start to vary. N equals 0, n equals to 1, n equals to 2. So then what you'll be able to get, you get when you take the sixth root, you should get all the 6 different roots. So I'm just going to summarize now because I do not want to explain. I've explained this earlier, but no, since we get this content. So we have the 6 different roots are what? So your 1 plus I, this one, and this one, they are all different. They are not conjugate of each other. Sorry, this one would be, yeah, they are not conjugate of each other. Okay. But once you include your minus sign over here, then you'll find some of them will get conjugate of each other. Okay. So what happens is that again, here you have the circle again, then the radius would be your root 2 here, okay, the absolute value here, and then your points are going to be distributed equidistant apart on that circle. Okay, so I think probably I should stop there before I get disconnected again. Okay, let me just stop there, and I already wanted to go into lecture 4 just to introduce things, but then probably I do that next week. Oh dear. No. Okay, okay. I'll come back just to get the attendance then. Okay. The video should be recording all my lecture there. Okay. So again, okay. Sorry guys, got disconnected again. You probably hear me a little bit bad now because I'm on data now. Can you hear me? Okay. So what I do now is just okay. What I do now is just take your attendance and that's it, and we'll end for today. Okay. Okay, I've done taking attendance. So thank you everyone. Sorry for all the disconnects. Okay, bye everyone.